Mic on. Hey, sometimes the mic would be off and I'll be recording. And then, to my amazement, I'll be like, where's the sound? So anyway, calculus, ne? Calculus. So, why do you think it's necessary to study calculus?
Calculus. Well, calculus is actually one of the most interesting topics I've discovered in math. It's very interesting.
Okay, why is that?
I don't know, there's just this one thing about it that makes it interesting. It's difficulty.
Like its difficulty level.
Yes.
Okay, let's move outside the difficulty and look at its usefulness in society. So sometimes you'd have like a tank, right? Or like a room. Let's say it's cold storage. You are a meat processor. Like this is the processing part of meat at a cattle ranch. Right? And now you're trying to figure out what's the best size storage for your operation. Okay? So that will depend. Let's say the height of the storage space is determined by the carcass. So are you gonna have a cattle's carcass or are you gonna have a sheep's carcass or a goat's carcass?
That's a very interesting question. I think I'll
That
have.
one. So if you have the cattle carcass, then the height's gonna shift. But also, how many you stack this side will determine the width. Yeah, one. And also, you need to take into account how you're gonna stack them this way in the storage space. Yeah, one. So by knowing the surface area or even the volume of the storage, you can use calculus to find where, if this area is a minimum, which would probably be best for that, and where this area is a maximum, and also the volume. So using that information, you are able to find the best possible size where you can stack either the most of one type of carcass or the most of another type of carcass, or even a blend of both, by knowing the maximum volume and the maximum surface area, or even the minimum volume and minimum surface area. So that's the end goal of understanding calculus, because it helps us make the most of what we have for applications in things like industry, etc. So that's the whole point of studying calculus in some aspects. So I'm speaking about it from an engineering perspective. Right, so the next important thing I want to start off with is the average gradient. Ne? Let's start off with a wheelchair ramp and a staircase. Wheelchair ramp, staircase, and maybe a hiking trail up a hill. Ne? There's the hiking trail up a mountain. Ne? Right, so I'll just put a theta there, just to show that even though it's not necessarily trig, we do acknowledge that this is an inclination. Yeah?
I see.
Yeah, and this is for, like, let's say maybe people who are struggling to walk up.
Old people.
Yeah, or people with special needs, right?
Mhm.
They have to go from one level to another level. Right? And yeah, so this is a ramp, this is a staircase. It's a bit high, isn't it? Can't go stadium.
Madaluna meladra, come on.
Yeah, and then that's a hiking trail, right? Alright, so when we think about the gradient, we often think about it as rise over run, ne? Which is how high you go over how far you travel, right? High deliberately because this refers to movement in the vertical plane, and far meaning vertical, horizontal distance meaning in the back and forth. So effectively, a gradient would be change in this direction divided by change in that, right? That's delta y and that's delta x. So that would be change in x and that would be change in y. Similarly, the case is the same on a hiking trail. Yeah. And now on an axis plane, we can have many functions. Some could be straight lines, some could be parabolic. But with a straight line, you would have, maybe let me use different colors for different functions, right? This one is with a negative gradient, and this one is with a positive. Maybe let me draw it this side so that I want to make it intersect as far away as possible from either axis. Yes, you see. Positive gradient and negative gradient. Sharp. And also with parabolic curves, hyperbolic curves, you can also have gradients, right? So you would have a negative gradient at a point there. And maybe somewhere there as well, that would still be negative gradient. And you would also have positive gradient somewhere there. And a positive gradient also there.
And here I thought when it's positive it would smile. It would smile.
Yes, the parabolic curve is smiling.
And when it's negative, it's a frown.
And I guess also on this curve, you would have negative gradient at this point. And if these were the other way around, then here you could have positive gradients on the hyperbola. You see? And here we would have positive, positive, positive. But on this flank, we'd have negative gradients. So that's more or less how we can visualize these gradients. And we can also apply this using the formula for gradient y2 minus y1
over
x2 minus
x1.
x1. So I prefer to start with the visual element because it helps us understand the more abstract nature of it. Yeah. And also I'm appealing to your nature as a guy because we're visual creatures, so maybe that would help.
Or visual creatures.
But also as a human. I guess it's a human trait. So if we have this formula for gradient, we can determine for various functions, we'll do this quadratic function. It's a quadratic function. And we need to find the gradient at x equals -4. So we'll say find m for that at x equals -4 and x equals -1. So as a hint, we're advised to use the equation of the curve to calculate the y values. So we'll start with y values. So at x equals -4, y equals 5 times -4 squared minus 4, which equals, that's 16 times 5, that's 50 plus 80,
76.
minus 4 is 76. And at x equals -1, y equals 5 times -1 squared minus 4, which is 5 minus 4, which is 1. Now, so gradient m equals y2 minus y1 over x2 minus x1. And when we substitute, y2 is 76 and y1 is 1. X2 is -4 and x1 is -1. This gives us 75 over -4 plus 1 is -3, which is -25. So between -4
and -1,
therefore, which is negative, let's note that. Therefore, decreasing. Let me just write decreasing. Therefore, it's a decreasing in this interval. So between -1, let me just write this. So between in the domain, I guess that's best, x -1, -4, -1, y is a decreasing function.
because it's negative.
Because the gradient's negative.
If it was positive, it was an increase.
Yes.
So those that are negative are always decreasing.
Yes, it's because this is what you would see if you were to plot it.
Mm-hmm.
You see, so for the same graph, we can also find for the following intervals x equals 2.5, and so we're gonna do an investigation like type thing. 2.99 y equals. So in this investigation, we want to see how the average gradient changes for the same function if we change the interval between 1 and 3 as we shrink. So somewhere on the x-axis, we've got 1, we've got 2, and we've got 3, right?
Mm-hmm.
Our interval shrinks from x equals 1 all the way almost to where it equals 2.99. The goal is to see what kind of behavior or activity happens as our gradient
It
decreases between the interval. Remember, if it's a curve, I could have our curve as decreasing. So our gradient would start out decreasing. Was it green?
Decreasing was blue.
It was blue. Okay. So we are first at an interval. So there's x, right?
Mm-hmm.
And we keep shrinking x1. So x1 keeps being shrunk like that along the curve.
Mm-hmm.
To the point where we're looking at the gradient at a specific point. And that's where we're going with the whole average gradient thing. Alright? So now we must find how the function y equals 5x squared minus 4 changes as we shrink our interval like this. Alright, so we've got, I'm supposed to have x equals 3. Alright, so let's substitute 5 into 1 squared minus 4, 5 into 3 squared minus 4, 5 into 2 squared minus 4, and then 5 into 3 squared minus 4, 5 into 2.5 squared minus 4, and then this one is 5 into 2.99 squared minus 4. Okay, let's start with the first one. On your calculator, how much is it?
Let me check for you, and it says abracadabra 1.
So for 1, it's 1, eh?
Mm-hmm.
And then for 3, it's 5 times 9 is 45 minus 4,
It's 41.
41. Okay, so I'm just gonna put 41 on each of the ones that have 3.
3.
5 times 4 is 20, minus 4 is 16. Okay, then do the ones studied 2.5 and 2.99 for us.
For the one of 2.5, it says 27.25.
27.25, okay.
And for the one of
2.99.
2.99, it says, wow, 40.705. 700, then at the end of the 700 there's a 5. It's separate. It's 7,000.
Oh, 7005. Okay, that's good data. That is very good data. So
Oh, it's very good data, because look at them.
So are you seeing now how these are starting to behave?
Mm-hmm.
So as we shift our gradient this way and we decrease the distance, it gets closer and closer to 41, which is the gradient at 3, which is the y value at 3, sorry. Not the gradient at 3, the y value at 3. So it gets closer to the y value at 3 as we decrease that distance in that direction, this distance in that direction. So much so that at 3, we can work out the gradient using calculus so that we find. So that's the whole point, finding the gradient at a point with calculus. That's a big part of the point.
I see.
Another example, we've got a function f of x. Function of x equals x into x plus 3, which I guess we could also say is x squared plus 3x. And we must find m equals y2 over y1 minus y1, sorry, over x2 minus x1. So we're given that function. And we must find the gradient, average gradient at x2 equals 5 and x1 equals 3. So I've already nominated them like that.
Mm-hmm.
That means at x1 equals 3, f of x equals, or rather, f of 3 equals 3 squared plus 3 times 3, and at x2 equals 5, then f of 5 equals 5 squared plus 3 into 5, which equals, so that's 9 plus 9 is 18, that's 25 plus 15, it's 30, 40.
You sure, or you just?
You can check for us. You can check.
It's 40.
You can check for us.
It's 40. We may continue.
Therefore, the gradient is y2 40 minus y1 18 over x2 5 minus x1 3, and that will be 2022 over 5 minus 3 is 2, which is 11.
It's right.
So the conclusion,
Therefore,
it's increasing. at that interval, it's increasing. All right. Did we work out the gradient in the last one?
The last one. Let me see. No,
Nah,
we
not
didn't work
really.
out the gradient.
Okay, it's fine. Let's quickly do that because that's an important thing. So I can erase this part, the visual, at least it's captured on video. So that's fine. Then what we can do is the gradient here is, so y2 will be 41 minus 1 over 3 minus 1, which is 40 over 2, which is 20. 41 minus 16 over 3 minus 2, which is 40 minus 16 would be 24. 25 over 1.
Yeah, we got the gradient for all of them.
Yeah, we got a 13. 41 minus 27.25 over 3 minus 2.5, which is 13.75 over 0.5, and that's 27.5. This one would be 41 minus 40.7005 over 3 minus 2.99, which is 0.300 something over 0.01, and that equals 30. Interesting data. So
And as of such, we have reached the conclusion of, well, the first graph, this one, it's increasing.
they're all increasing here. It's the same interval.
There's no, I thought there was a negative one that would cause a decrease.
No. No. So, yeah, so long and short of this exercise, can we calculate the gradient of a curve? That's the question we're asking. Right. The average gradient between 2 points on a curve equals the gradient of the straight line through the points. For which one is this now? Oh, yeah, it's for that curve we have 5, what is it? This one we were doing. 5x squared minus 4, ne? So for the curve we have 5x squared minus 4. Let's say it looks something like this. Just make a quick sketch. 0, 0.5, 1, 1.5, 2, 2.5, 3.0. And then here would have 0, 3.
Is it necessary for them to be on a first decimal?
12. Well, it's just to show that they are acknowledging that there are decimals in this case. 12,
Okay.
15, 18, 21. that's a little bit too small. 3, 6, 9, 12, 15. Also a little bit too small. 3, 6, 9, 12, 15, 18, 21, 24, 27. All right, so I think I should move this one here. So it comes after this slide.
Okay.
All right, so we've got values of y that go up to 27, right? 27.25 corresponds with 2.5.
Do you think we were right to leave it at 27? Shouldn't we bring out the max value or something?
It's already done. So let's say what's the 3 maps to the 27. Oh yeah. I think you had a point there, but I want to do this like this. So there's B and there's A. Ne?
A is on which point? 1, 0.
1, 0 maps to 3.
Okay, and then B is on 27 to 3,
to 3, 0. Alright, so that means if we move between A and B, our gradient is between those 2 points. Between 2 points. Still keeping the thing at B, if we move to like 1.5, when it goes back to that visual that I was making before that other example. And that means if we move towards 2 point something, starting there, the gradient decreases until at a point it's a tangent to the curve. Just as you would have tangent to a circle. And this is a nice...
A tangent to a circle touches the circle once, right?
Once.
So a tangent to a curve, what does it do?
Touches a curve once because it's a curve.
I see.
So even if you zoom in so much, you'll zoom into the point, at the point exactly where the tangent and the curve meet. At that point, you'll find that your curve's like that and your line is also like that.
They're gonna be like, hi, I'm tangent, what are you? I'm curve, we just met.
Yes. But they get so close. And that's something you kind of get to experience when you're using computer-aided drawing software. So if you have like a circle and maybe there's a tangent to it, and then you zoom in into this point, you zoom into it so much, then it ends up looking like it's 2 lines at some point.
Oh.
Yeah, that's the illustration.
I see.
Now we can use the same concept of gradient for physics. And how do we do that? We use average rate of change.
Average rate of change.
Yes. Remember in science, the speed is the rate of change of distance. So it's how much distance you cover in how long.
That's time.
Yes. How far do you travel in how long? That's how fast.
I always say time is the rate taken for a certain.
Time is time. Rate now uses distance relative to time.
That's what I was gonna say in time. I
Time
always say
is
that
time.
time is a rate of which a certain object reaches a certain
It's the
point
duration.
of distance.
Time is a duration. So if we look at speed, speed is simply how fast, how fast you're traveling, how fast. And how fast is a measure of, if you travel, you're traveling over a distance, right?
Mm-hmm.
How much ground you cover, how much distance, or let's rather say how far, keep it very basic, how far over,
How long?
I don't want to say long because that could also mean distance. It's like,
Oh.
You're talking about space and time, so I don't want to say how long because it sounds like that. But if you say over how much time,
Just say time. Don't say how much, just say time.
yes, time. So the distance you take over the time.
Mm-hmm.
All right, so the average rate of change between A and B is shown in a graph. I guess same as the one before.
Guess now you gotta demonstrate once again.
Yeah, I guess the same as before, right? But let's say for argument's sake, there's a point 3 and 1, x equals 3 and x equals 1. And at x equals 1, y equals 3. And at x equals 3, y equals 27. That means the rate of change, which is also a gradient, the rate of change of the curve
That 3, is it positive or negative?
is positive.
Okay.
So we'll have 27 minus 3 divided by 3 minus 1, which is 24 over 2, and that's 12. If the distance traveled in meters, which is a function s in terms of time, because it changes over time, and that function is t squared. T is time in seconds. Then what is the average speed between the 3-second mark and the 5-second mark? Then at t is 3 and t equals 5, then s of 3 equals 9 and s of 5 equals 25. Therefore, the velocity over that time interval will equal the rate of change of displacement at 5, which is 25, minus that at 9, divided by 5 over 3, 16 over 2, and that is 8 meters per second.
Why must we always leave things in meters?
It's the basic unit of measuring distance or length. It's the primary unit we measure linear distances with. and also curved distances.
For curved distance, this is impossible to use, I don't know, kms.
Kilometers, you still can. Kilometer just means you're moving. It's a kilometer equals 1,000 meters.
Mm-hmm.
So that's like 10 to the 3 meters. So that means if on a scale, let's say we've got meters,
Mm-hmm.
then we've got kilometers, then we've got, as we increase, the order. And then millimeters would be one. So that's what that means.
I see.
Alright, so derivative of a function at a point. So that whole exercise we were doing, of finding the gradient at different points, and then between different points, and declaring if it's increasing or decreasing. That whole exercise, the point of it was so that we can get to this part here where we define the derivative. The derivative, right?
When h approaches 0.
Yes. So 3, derivative of function at point.
I've never been a fan of derivative.
I think you just need to give calculus a chance. It's very exciting in my view. Right, so those two things that we started with, I think we started with gradient, average gradient, and then we went to rate of change, isn't it?
Distance over time.
Rate of change, So now we're gonna discuss derivative of function. And they use the word function deliberately because it can apply to straight lines or curves or whatever. Circles, ellipses, at point. So these are feeding into each other like this. So now what happens is if we have a function, it's y equals f of x. Then its derivative, or how we differentiate it so that we can get the slope. We say then y prime equals f prime of x, and that equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. And now this is intentional because remember that example with the 2.99. With that example, you had 2.99 and 3.
Yes.
We get closer and closer and closer to the gradient at 3. So that means if we increase the number of 9s here and had 2.999, then we would get a number larger than 30. And if we increase the number of 9s there, we would get a number larger than that number that's larger than 30. And the closer and closer we get to 3, the closer and closer we get to like a number that we can't go past.
Can't go past what, 30?
That's closer to here. So we can try the same computation. Let's do on your calculator,
Okay.
On your calculator, we'll have, let's say, it's 5 times 2.999 squared minus 4 Oh, no. It ought to be 41 minus. What do I want to say? Hey man, you understand this calculator?
Yeah.
I want you to punch in this function, this
Uh-huh.
gradient, king this tricky, but
Mm.
we're gonna keep changing these so that we have more 9s going in that direction.
So what? I add more 9s?
Yes, more 9s after the decimal.
I add 3 9s. Is that enough?
Yes, 3 9s. And then the next round we're gonna do 4 9s. The next round 5 9s, etc.
This is how much we get with 3 9s.
With 3 9s, it's 40,
Yeah.
comma 97.
Yeah.
So it's getting closer to when x is 3.
Yes.
Then find out the gradient and let's work out how much that is. So let's say negative answer plus 41. So we need to divide that by 3 minus 2.999. And that gives us 29,995. Okay, that's cool.
That's a really good approach to 30.
So it's 29,995. Okay,
Yes.
let's do with 4 9s.
With 4 9s.
Yeah,
Okay.
let's try with 4 9s.
It's gonna be 5. Oh my god. 2, 4 9s. There we go. Minus 4. There we go. 40,997. The 7 moved this time.
Okay.
It's at the third.
So negative the answer plus 41. And then divide this by 3 minus 2 point. It's 4 9s.
Yes.
4 9
Equals to. It's still the same. Is it at a constant? No, it's not the same.
It just keeps going closer and closer and closer to 30.
Oh.
Yeah, what?
Does it reach a point where the number is constant?
At 3, it's 30. But just before 3, 2 point an infinite number of 9s before 3. It gets 29.99999 infinite number of times 5. And then, like, just to show, it goes closer and closer and closer and closer and closer to 30, but it never gets to 30.
Okay, so it's a constant.
At 30, then it means constant. But if you keep getting closer and closer and closer to 30, it still remains an irrational number like this.
Okay.
Yeah. So that thing is intentional because if we have 0 here, this thing is going to be undefined.
Yes.
So this is intentional because
But
that is
wait.
our limit.
Wait. Tell me if I'm wrong. If we have 0 here, right? And here is also 0 because they say h when h approaches 0, h will be 0. Don't
It's
they
fine.
cancel each other?
They don't cancel each other per se. But if
Okay.
this just becomes blatantly 0, you'll have f of x there, but here you're going to have a numerator of 0, a denominator of 0. And when you have a denominator of 0, calculator, we can't make sense of it.
This was an illegal move I used in the examination. Ugh.
Yeah, so...
But then it didn't cost me a mark. It actually gave me a mark.
So what you have to do is to work out for some time f of x plus h and f of x. Alright? And then at a certain point, once you've worked out that, then you can substitute whatever h is. So from first principles, so this is called first principles, right? This is the basis of calculus, right? So we've got f of x equals negative 3x squared. Negative 3x squared. Alright. So we start first by finding f of x plus h, and this is negative 3 into x plus h squared, which is negative 3 into x squared plus 2xh plus h squared, and that equals negative 3x squared minus 6xh plus, oh no,
I forgot the minus.
minus 3h squared. All right. And this is yeah, so then we can substitute this into this. It's the limit as h tends to 0 of, we substitute that into here. So we have negative 3x squared minus 6xh minus 3h squared minus negative 3x squared over h. And this gives us negative 3x squared minus 6xh minus 3h squared plus 3x squared over h. And then these are additive inverses, so they subtract each other out.
Because
so
they're additive inverses.
Inverses, yes.
Any additive inverse must always cancel each other.
A good way to think about additive inverses is, what must I add or subtract to this number to get 0?
Oh.
And then multiplicative inverse is, what must I multiply this number with or divide it by so that my result is 1? And then here you can simply take out the common factor, which is h. So it's h into negative 6x minus 3h divided by h. So we still have that limit, ne?
You want to know how I'll take it from this point? Wait, you haven't used the limit? No, we used the limit.
Yeah, I must use it consistently throughout. You see? So now that we've taken the common factor of h, then they're multiplicative inverses of each other, so they give us 1. And then the limit as h tends to 0 of negative 6x minus 3h is what we're left with. And now when we substitute 0
at minus 3h, which means 3 times 0 equals to 0.
Yes, then we're just left with f prime of x equals negative 6x. So when we substitute that 0 there, and we get rid of the limit, the limit vanishes because we've substituted it into the 3h. That gives us 0, and we're just left with f of x equals that. So let's quickly do this example. F of x is 5x squared minus 4x plus 2. So we must find f prime of x. So we'll start first by finding f of x plus h.
F of x plus h?
Yes, so where we see x, we plug in x plus h. So we'll have 5 into x plus h squared minus 4 into x plus h plus 2. And then this gives us 5 into x squared plus 2 xh plus h squared minus 4 x minus 4h plus 2. So that's 5x squared plus 10xh plus 5h squared minus 4x minus 4h plus 2. So there are no factors which we can say we can eliminate. So then we can just substitute f prime of x equals the limit as h tends to 0 of, I'm just gonna go right ahead and write because I've already declared the equation up here. So since it's there, I'll just substitute and go with 5x squared plus 10xh plus 5h squared minus 4x minus 4h plus 2 minus 5x squared plus 4x minus 2. All of this is over h. As h tends to 0, this gives me, so I'm going to look for additive inverses. It's 5x squared. It's 4x. It's 2. Yeah, 1, 2, 3, 4, 5, 6. So that's even. So I'm just left with 4h, 5h squared, and negative 10hx. All right, so
Why did it turn negative though?
Why did they turn negative?
Yes.
That is a good question. That is because when we have negative f of x, as we do here, we are supposed to say it's negative into 5x squared minus 4x plus 2, because this part is f of x. And then this in turn gives us negative 5x squared plus 4x minus 2. And that, this portion here is this portion here. Do you see?
I see.
Right, so we're left with 10xh plus 5h squared minus 4h over h. So I'm just rewriting this part just so I can make sense of what's going on as I'm working on this. All right, then I take out the common factor of h. So I have 10x, I have 5h, and I have 4. And now at h equals 0, at h equals 0, then f prime of x becomes 10x minus 4. So I've taken out the common factor of h. That gives me multiplicative inverses. Then I get 1.
You have arrived to 1. 1 is your destination.
Yes, then I substitute h equals 0, and then we land there. Here's another interesting one, another example. So f of x is a hyperbolic function 2 over x. So that means f of x plus h would be 2 over x plus h. And we must find f prime of x, which is the limit as h tends to 0 of f of x plus h minus f of x, that is over h. So we must first find I guess we can do that. Alright, so this one gets interesting there.
How so?
So automatically we'll have the limit as h tends to 0 of 2 over x plus h minus 2 over x. Now how do we make so that we have the same denominator so we can work with these fractions here?
Which ones?
These are fractions here at the numerator. Right? Oh yeah, there we go. So these fractions, we need to make them have a common denominator or something that's close to work with.
A common. They both have x though, and this one plus f of y h. And we already know that h is 0. Why don't we make them 0, which is going to be... Is it going to be impossible? My teacher once did this, you know.
Remember,
impossible.
at this stage, when h is 0, this thing becomes inexplicable. So you don't want that. So you can say a common denominator for 2 over x plus h is x into x plus h. That's the lowest common multiple of these two. Remember, when you have 2 over 5 plus 1 over 4, the lowest common multiple is the product of these two. Else, if the larger one can be divided by the smaller one, then it's the larger one.
Okay.
So the product of the two is 20, because 20 is also 5 times 4. And how many times does 5 go into 20? It goes 4 times. 4 times 2 is 8. 5 times 1 is 5, and that gives you 13 over 20. Remember? That's how we add and subtract fractions. Same way, we do this. So this goes x times, so that's 2x. That goes x plus h times, that's 2 into x plus h, and that is 2x minus 2x minus 2h over x into x plus h. Alright? And that gives us negative 2h over x into x plus h. This is divided by h. So we can just then this becomes oh yeah, I want to remove that. So oh yes, now the fun part. Remember, this is a fraction again, and it's a numerator. This is also a fraction, which is a denominator, right? So in this case, we've got fraction divide by fraction, and this means the numerator gets multiplied by the inverse of the denominator. So that being said, the limit as h approaches 0 of that becomes negative 2h over x into x plus h times 1 over h, because this rule applies there.
I see.
Then we end up having, these are multiplicative inverses, so we're left with h tends to 0 of negative 2 over x into x plus h. Okay?
Mm-hmm.
Then when h goes to 0, we're left with f prime of x equals negative 2 over x times x, which is negative 2 over x squared. Right. So this is first principles. And now we learn this so that we can understand the process that leads us to how we differentiate. So how we differentiate, we use, if we have y prime equals f prime of x. We can also have, so if f of x equals x to the power n, then f prime of x equals n into x to the power n minus 1, which is what first principles has shown us. Remember, in our previous example, we had f of x equals 5x squared minus 4x plus 2, and we've also had f of x equals 2 over x, which is 2x to the power negative 1. So at the end, we found that f prime of x equals 10x minus 4, and here we found that f prime of x equals negative 2x to the power negative 2, which is negative 2 over x squared. Remember these two that we just did now? And this one.
Which one's that one?
This one, its derivative was 10x minus 4. Because we take the exponent, we multiply it by the constant, and then we subtract 1 from the exponent. And we do that with every term that has x in it. And ultimately we get there. So if we take 5 and we multiply it by 2, we get the 10x. And if we take the 2 and we subtract 1, we get the x. And if we do that with the 4, it's 1 times negative 4, which is negative 4. And then it's x to the power 1 minus 1, which is x to the power 0, which is just 1. And then this one doesn't have x, it's x to the power 0. So 0 times 2 is 0. Then that constant falls off.
Oh, yes, it's like electricity. It leaves.
And you could call it however you want, but the logical way to think about it is like this, yeah. So here we've got negative 2 divided by 2, x squared, ne? So if we think about this as 2 to the power x minus 1, then if we have negative 1 times 2, that's the negative 2. And if you take negative 1 minus 1, we get negative 2. So we will have negative 2 x to the power negative 2. And that's the same as negative 2 divided by x squared. So yeah, one of these derivatives are like this, né? So from first principles, we've worked out how we do them. And now we're going to do the same, but without using first principles. So the first thing that we're taught is that this is the case when you differentiate for a function that has x in it. And if we're differentiating for a function that is just a constant, then f prime of x is 0, where b is a constant, né? Then the derivative is 0. Where f of x is a function of x, then we work it out like this, with n times x to the power n minus
1. We're gonna use that one.
Yeah, another way to differentiate is to use d, the differentiation of, or the derivative of f of x, or the derivative of the function or sum of functions, really, right, with respect to x. So then we have other rules. This is rule number 3. If we have two functions being added together, then their derivative is the same as the derivative of the first function plus or minus the derivative of the second function. And also, if we have functions multiplied by a constant times f of x, this is the same as the constant times the derivative. So don't worry about these rules yet. But you can look at Mind the Gap, which I've sent invite to Google Classroom there. Just check it out, so you can see these notes. You can look at them in your spare time. But yeah, these are the examples where you can do that. All right, so we must find in the next example. Am I going too fast or am I going at the correct pace?
You're going at the correct pace.
All right, cool. So, okay. And then I just want to write this problem statement. So f of x is 3x plus 2 times x minus 5. What do you think is the first thing we're going to have to do here?
We're gonna have to. The first thing that we have to do.
Before we can find f of x.
Before we can find f of x, don't you gotta differentiate them first?
Differentiate? That's finding f of x. So before we differentiate, what do we have to do to this expression here?
Break it down.
Break it down how?
I mean, you can fill up the x.
What do you mean fill up the x?
Is it possible?
It's straightforward what we have to do. These are factors of a function, of a quadratic expression, aren't they?
They are.
So if we want to get a quadratic expression, that gives us then the function. And we are quadratic or cubic or whatever function. So we need to express this in a way where we have a function that has that.
Is it a must?
Yes, because how are we going to differentiate it here? Because the rules for differentiation, they only allow us to add derivatives of different functions, and they also make provision for when a function is multiplied by a constant, not when a function is multiplied with another function.
Oh.
So we don't have that provision here as one of the rules to do differentiation.
I see.
But this can be expressed like that. So we need to express it like that. Because when we have, then we can use this rule to differentiate.
Wait, how are you going to be able to put it in a form of which we can use to differentiate?
Okay,
You just gonna jump straight to quadratic?
f of x. It's a good question that you're asking. But let me ask you this. What if you distributive rule? You apply distributive rule.
Step 1, step 2.
Yeah, so if we do that to this, what do we get?
3x squared
Uh-huh.
minus. Wait. Okay. Where is it sure that it's 15? Oh yeah, 3 5 equals 15. 2 times 2 times 10. 2 times 1 is 10. You minus with, but then it's positive here.
Yes, which one is the larger number?
15.
So which sign will our answer take?
The negative from 15.
Yes. So it's a difference because the signs are different.
Mm-hmm.
So we take the difference, it's 13, but the sign that's larger is the bigger number.
Okay.
So then that means f prime of x will become 6x minus 13.
What happened to the 10? It fall off?
It fell off because if we differentiate using this, you see this rule?
Mm-hmm.
You take the n, you multiply it as a coefficient. So you take the 2, you multiply by the 3, you get the 6.
Mm.
And then you subtract 1 from the original exponent. So 2 minus 1 gives you x to the power 1.
Mm.
You do the same here. 1 times negative 13 is negative 13. 1 minus 1 becomes 0.
Yes.
And x to the power 0 is 1.
Oh, I see.
Right? Here, we already have x to the power 0. So what happens? You have 10 times 0 times x to the power 0 minus 1. So you're going to have the 0 times 10, which already gives you a 0.
Nothing.
So anything that you're going to multiply it with is going to give you a 0.
Mm.
That's why it falls off.
I see.
So with surd signs, you can simply write them in the exponent form. That way,
Oh, so that's what they mean when they say leave your answer in surd form.
yes, surd form is that little car looking thing.
It's a house.
Yes.
Ish, thinking about the way I wrote my paper one. Yes.
So you're having two minds about calculus, how it went,
Mm.
because of what we're doing now. And compared to how you're learning in class, what's the difference?
They don't explain everything in class. He just explains what is needed.
The reality is that maybe your teacher's thinking, these kids are going to go to varsity anyway, so it's going to be behind them saying, do this, do that. That's fine, I guess. But also, I guess for you it helps to have someone who can help you study. So what you can get from here is there's a specific way to doing calculus. And all that it teaches us is just to
Oh my god.
it's to think
It broke.
it's to think a little bit further than what we know from algebra and everything else. Yeah, well, that's what at least I'm sensing from it. Alright, so we can do these examples. So this is the third form, and this is exponent. So we must always work in exponent form, ne? During calculus. Then we have a function. whose derivative must be sought. So we must find the derivative of x cubed minus 2 to the power 2. So with this example, what we would have to do is multiply out. So we have x to the power 6. It's that squared. That times, so x cubed times negative 2 is negative 2x cubed, and times 2 is it's negative 4x cubed, and then negative 2 squared is plus 4. So that's the expression written out in full. So now its derivative then becomes 6x to the power 5 minus 12x squared. No, wait.
Yes, it is squared.
And then that falls off. What I'm not understanding is...
Didn't you say that the exponents... Wait, what do we call them exponents? These squares?
Yes, they're exponents.
Yes, the exponents. We gotta minus them by 1.
Hold up. What did I do? It's not 2, it's 3. That's why my thing looks so weird. It's not 2, it's 3.
What looks so weird?
No, my end result doesn't look like the one that we're working on. So if it's 3 there, so this becomes 9. So that becomes negative 3x cubed times 2 is negative 6x cubed. That's correct. Then this is why it didn't look So then 3 times negative 6 is negative 18. 3 minus 1 is 2. And this is this is the derivative. A second example.
The 9 fell off.
You could say that. So our next function is f of x equals the cube root of x, and this equals x to the power 1 over 3. Because we must work with exponent form. Then this means f prime of x will equal 1 over 3 times x is 1 over 3 x, and 1 over 3 minus 1 is 3 over 3. Oh, no. It's 1 minus 3. Minus 3 over 3, and that gives us negative 2 over 3, which is 1 over 3 x squared, like that. C.
I see.
We've got dx of 3x to the power 5, which is the same as finding dx of x to the power 5 over 3. That is because if you have a number mn, this is the same as x to the power m over n. Yeah. So then dx of x 5 over 3 would be 5 over 3 x. We have 5 over 3 minus 1, which is 3 over 3. That's 2 over 3. 2 over 3, and this equals 5 over 3 x to the power 2. Are you following, youngster?
Yeah, I'm following.
Alright, cool. But these, you remember these principles, right?
I need to remember them.
This is from our grade 9 work. Grade 9, grade 10, exponents. Ne?
Oh, dealing with exponents.
Yeah, this exponent third form. Grade 9, grade 10. Grade 9, grade 10. So remember that, ne? That's why when you move from here, x to the power 2 over 3, you get to a third form of the cube root of x squared. Then we must differentiate. So the next two examples, which are also third form, you still work with them like that. You convert the thirds to exponents, and then you work with them like that. And then other examples also include, if you have fractions like 3x squared over 4x cubed, this equals 3 over 4x, or 3 over 4 times x to the power negative 1. So then the derivative becomes negative 3 over 4 x to the power negative 2, which is negative 3 over 4 x squared.
And just like that, you're done.
And just like that, you're
How
done.
many marks does it offer?
That's like 1 or 2 marks like this.
In an examination.
In an exam.
Wow.
1 or 2 marks for this. Here we would have y equals.
God alone knows what happened that day.
Here we've got y equals square root of x over 2 minus 1 over 6x cubed. So we can write this as a half x to the power half minus 1 over 6 x to the power negative 3. Therefore, dy dx equals 1 over 4 x a half minus 2 over 2 equals negative a half. So that gives us negative 1 over 2 minus or plus negative a half.
These messages, I think it might be my mom.
Probably.
Let me check on.
Negative 4. And this equals 1 over 4 square root x plus 1 over 2 x to the power 4. Oh, it's actually I have something up there. Sure.
Even here.
No, it's not alone. It's
Even here, it's my mom. No.
alright, cool. So just like that, you're done. Next frame.